Back in the early 20th century, the young astronomer Edwin Hubble joined a larger quest to understand the scales of time and distance that define our universe. To make his measurements, he observed stars in the nearby Andromeda Galaxy, just 2.4 million light-years away. His namesake, the Hubble Space Telescope, has extended those measurements to the far limits of time and space. In its legendary deep field images, Hubble stared into seemingly blank regions of sky, revealing thousands of faint galaxies from the early days of the universe. These blotchy collections of stars are infant galaxies. Over the 10 billion years their light has traveled to reach us, some may have evolved into galaxies that resemble our own. With a supermassive black hole in its center, spiral arms, exploding stars, solar systems, planets, and perhaps even life. Hubble has shown that our Milky Way galaxy is a dynamic cosmic laboratory. Some of its most striking and beautiful images are giant structures known as nebulae. This one is nicknamed Horsehead, after its clear and curiously familiar shape. Rising from a sea of gas and dust, this so-called dark nebula is a cold, dusty cloud set against a background of glowing gas. Then there's the famed Eagle Nebula, nicknamed the Pillars of Creation. A group of hot young stars is scouring these luminous towers with fierce winds of energetic particles. Dense pockets of gas resist these winds. Within them are cocoons of gas and dust, where new stars are being born. You can see the same process underway in the Monkey Head Nebula, about 6,400 light-years away in the constellation of Orion. The Monkey Head is a stellar nursery with all the ingredients needed for star formation. Its peaceful beauty masks the violent events within it. In places where stars are able to form at high rates, Hubble astronomers have zeroed in on the moment of birth. One team has been collecting high-resolution Hubble images of energetic jets of matter being shot from newborn stars. Unlike most astronomical phenomena, which can appear motionless over centuries of time, these jets visibly change on human timescales. Using Hubble, astronomers can see knots of gas brightening and dimming. This shows that these jets are not being launched in a steady stream. Rather, they are racing out sporadically in clumps. The irregular structure of these jets is likely caused by material that periodically falls onto an infant star. This image shows how violent the end stages of star formation can be. In the constellation of Cygnus, a few thousand light-years away, lies a compact star-forming region called S106. A young star named S106IR is being born at the heart of the nebula. In the final stages of its formation, the star is ejecting material at high speed, disrupting surrounding clouds of gas and dust. 3D visualizations show the extent to which the star has carved its surroundings into a complex shape, including hollow cavities. At the outer edges of these cavities, the gas has been compressed into shock fronts. The material spewing off the star not only gives the cloud its hourglass shape, it is heating it up to temperatures of 10,000 degrees Celsius. The star's radiation excites the gas, making it glow like a fluorescent light bulb. A star is born when pressure and heat in its core cause hydrogen gas to undergo nuclear fusion. The heat generated by this process pushes outward, countering the inward pull of gravity. From the violence of their birth, most stars spend their lives shining in relative peace, gradually using up the hydrogen fuel that makes up their cores. Smaller, cooler stars are incredibly efficient. A red dwarf, with 10% the mass of our Sun, can burn for 10 trillion years, almost 1,000 times the current age of the universe. By comparison, larger, hotter stars like our Sun burn more quickly. At about 5 billion years old, our own Sun has gone through half its expected lifespan. By observing stars similar to the Sun, scientists now have a good idea of what will happen to our solar system in the distant future. The Sun will grow steadily hotter, causing it to swell into a so-called red giant. When the Sun does this, it will destroy the inner planets of the solar system. Next, the outer layers will puff out, forming a dense cloud of gas and dust that will obscure the visible light from the star. In this stage, it forms a protoplanetary nebula. Only dim infrared emissions from the dust cloud and reflected starlight let astronomers see anything at all. Hubble images of this stage show a wide variety of shapes, hinting at the complex dynamics at work inside. The spiral structure of this nebula is particularly unusual and is likely due to a second orbiting star that is producing swirling patterns in the gas and dust. Over a period of a few thousand years, radiation from this hot remains of the star excites the gas in the nebula, causing it to glow. The once faint nebula now becomes a bright and mysterious cloud called a planetary nebula. This type of nebula populates our galaxy with luminous shapes that draw the gaze of many a skywatcher. Eventually, planetary nebulae fade to nothing as their gas and dust diffuse into space. All that remains is the tiny white dwarf, a form that our Sun will take billions of years from now. Planetary nebulae are more than just beautiful shapes that grace our galactic skies. They show important stages in the life cycle of stars and how they interact with and even shape their surroundings. Hubble has given astronomers the sharpest views yet of these ghostly, dynamic structures. Take the Ring Nebula, just over 2,000 light-years away from Earth. From Earth's perspective, it looks like a simple elliptical body with a fuzzy boundary. But Hubble observations show that the nebula is shaped more like a distorted donut. The donut hole may look empty, but it is full of lower-density gas that stretches toward and away from us, creating a shape a little like a rugby ball that's been slotted into the donut's hole. The space surrounding the nebula is turbulent and full of knotty structures that formed long ago. If we were able to rotate the ring nebula by 90 degrees and view it side-on, it would look more like the nebula M76, also known as the Little Dumbbell. In the act of dying, sun-like stars cast most of their mass out into the galactic winds. In time, the atoms in our own sun may well be swept up into new suns, new solar systems. In the cycles of star birth and star death, the galaxy is dominated by a rare and extremely violent breed. Stars 10 times the mass of our sun, and even larger, burn hot and fast. Intense temperatures and pressure ignite nuclear fusion reactions in their cores. Hydrogen gas turns to helium, oxygen, carbon, calcium, silicon, all the way to iron. The outward pressure from heat radiating from the star's core of the 200 million odd stars in our galaxy, one goes supernova about every century or so. The last one to be seen in the Milky Way, supernova in recent years, appeared in 1987 in the large Magellanic Cloud, a dwarf galaxy just above the plane of the Milky Way. It was so bright, it was visible to the naked eye. Launched 3 years later, Hubble has been tracking the evolving spectacle for over a quarter of a century. Astronomers have marveled at the complexity of the explosion, including the patterns etched by its expanding shockwave. Even though a supernova is only bright for a short period of time, the dusty clouds it leaves behind can last for millennia. Their effect on the surrounding interstellar gas lasts even longer. Although no supernova in our galaxy has ever been observed with a telescope, plenty of supernova remnants have been. Hubble's sharp images of their complex structures help explain the sequence of events, as well as the profound impact these explosions have on the galaxy. Take the Crab supernova, one of the most interesting and most studied objects in all of astronomy. Japanese and Chinese astronomers witnessed the explosion in the year 1054. The filaments shown in these images are the tattered remains of the star, consisting mostly of hydrogen. The collapsed core of the star embedded in the center is barely visible in this Hubble image. Yet you can see its effects. The bluish glow comes from electrons whirling at nearly the speed of light around magnetic field lines that extend from the star's collapsed core. Astronomers have been poring over the nebula itself, still growing at a rate of 1,000 kilometers a second. What they've found is that the filaments of matter that roared out of the blast contain large volumes of dust, an array of mostly carbon or silicate compounds that absorb visible light. These solid particles are crucial for the formation of solar systems. Within the Crab Nebula, there is enough dust to make 30 to 40,000 Earths. Galaxies all around the universe bear witness to the dusty legacy of countless supernovae. The bright central region of the famous Pinwheel Galaxy, for example, is surrounded by dark, dusty lanes. In spiral galaxies, hot winds from exploding stars have helped push those clouds toward the periphery, as well as above and below their flat disks. You can see evidence of this in our view of the Milky Way galaxy. Dark dust lanes and ominous clouds dominate our view into the disk, while tendrils of dust reach far above it. Some dust clouds are destined to light up with new stars, as you can see in one of the Milky Way's small companion galaxies, the large Magellanic Cloud. Its most dramatic feature is the Tarantula Nebula, a bright region of glowing gas and energetic star formation. The tarantula, shown in these Hubble images, glows brightly because hydrogen gas within it is being excited by ultraviolet radiation from newborn stars. In a wider view, the luminous Tarantula Nebula stands out from its host galaxy. It is the brightest known star-forming region in the local universe and one of the most attractive spots in the night sky.